Hello everybody. Today I am on the lecture 2 of module 3, and if you recall my last class that I started the Levy's formulation for rectangular plate, which is by nature and provides an exact solution of the plate differential equation, and in that connection we have seen that Levy's formulation can be done with the help of single series, and then the convergence is rapid, but it is applicable for certain condition that when the two opposite edges of the rectangular plate are simply supported, and other two opposite edges may have same condition or may have different conditions also. But thing is that when this condition is not met directly, then Levy's condition cannot be applied. So, let us see how we can explore the Levy's formulation to solve other plate problems, that means plate subjected to other type of loading. In the last class I have discussed the problem which was already solved by Navier's method, that 4 edges were simply supported. So, in that case we applied the Levy's condition and we have found that the result obtained is was closely in agreement with the Navier's method. Okay. So, today's lecture that outlines will be highlighting the important steps of Levy's method for rectangular plate, comparison of Levy's method with the Navier's method for rectangular plate. Then we will illustrate a problem of rectangular plate whose two opposite edges are simply supported and other two opposite edges are clamped, and which the plate carries uniformly distributed load. Okay. Then we will do this problem that two opposite edges are simply supported and other two opposite edges are clamped, carrying partially distributed load, partially covered uniformly distributed load. Okay. In the first case the edges are clamped on two opposite edges, and here also the edges are clamped, but difference is that in the first case the full plate was loaded, in the second case the plate was partially loaded. Okay. Then we will study the plate with two opposite edges simply supported and other two edges are clamped, but carrying strip loading. So, that type of loading is sometimes encountered in case of brick wall that is constructed over the slab directly, not transferring the brick load on the beam. So, in that case the analysis of the plate for the line loading is important, and we will discuss this strip loading on the rectangular plate. Then some more examples of rectangular plate I will try to show you and how it can be tackled in a different situation. Okay. So, Levy's method I have told that it gives the exact solution. Navier's method also gives the exact solution, but the difference is that Navier's method, the requirement is that all the 4 edges of the rectangular plate should be simply supported, but in case of Levy's method some relaxation is made, that means only these two opposite edges required to be simply supported and other two edges may have any boundary conditions, okay, may have same boundary conditions or may have different boundary conditions, or may have this elastically supported edge or this supported by torsional spring as support. So many conditions may exist, but it can be tackled by Levy's method when two opposite edges are simply supported. The most fundamental thing in Levy's method is that the deflection is assumed as a sine series, that you are seeing that we have to assume the deflection surface as single sine series. The summation extends from 1 to infinity, and the summation is done that the deflected surface is taken as a function of y multiplied by a sine function sin m pi x by a. here it is sin m pi x by a, because the x edges, the x is equal to 0 and x is equal to a. That means, edges parallel to y axis are simply supported. So, therefore, sine function is taken. You can see that the taking sine function, it renders the boundary condition to be satisfied at x is equal to 0 and x is equal to a edges. That is, curvature along x direction is 0 and then your deflection is 0 at the edges x is equal to 0, x is equal to a. So, by taking this deflected surface, this function, we have proceeded to satisfy the differential equation of the plate, which is fourth order partial differential equation, and you know that differential equation in compacted form is del 4 W equal to q x y divided by d, where d is the flexural rigidity of the plate. It is given by E h cube by 12 1 minus mu square. Okay. Now, after substituting this deflected function in the differential equation del 4 W equal to q by d, we actually arrive at this ordinary differential equation, d to the power 4 y m y dy to the power 4 minus 2 m square pi square s square d square y m dy square plus m to the power 4 pi to the power 4 divided by a to the power 4 into y m y equal to f m y, where f m y is a function of y. How this function is produced, that can be understood by when I take the substitute this function to the original differential equation, and then after multiplying both sides by sin m dash pi x by a, and then using the orthogonality condition of the sine function, we can arrive this differential equation with non-homogeneous term, which becomes a function of y. Because the integration is actually carried out with respect to x, here you can see it, then because of integration with respect to x, the result will not contain any x variable. So, it will be a function of purely a function of y. So, this differential equation you are seeing that it is a the differential equation with y. Okay. So, that differential equation has been solved with repeated roots that are found for the characteristic equation with for the homogeneous solution, and then we have found that the solution is given for the homogeneous part as this function, that is a m b m y cos hyperbolic m pi a by y plus c m plus d m y into sin hyperbolic m pi a by y plus the particular integral or particular solution. That integral is to be found considering the forcing function in the left hand side. If there is a no force load acting on the plate, then this function will be 0. Okay. Now, you can see the characteristic of the general solution of this equation, equation number 1 here. You can see here that a m, b m, c m, d m are arbitrary constants that have to be that can be found by imposing the boundary condition on other two opposite edges. That means, y is equal to 0 and y is equal to b edges if the size of the plate is a cross b. Okay. And then this origin is taken at one of the corners on the left hand side. Okay. So, W p is the particular solution that depends on the nature of loading. But one interesting thing you can see here, that cos hyperbolic m pi a into y, it is a symmetric function, and sin hyperbolic m pi a y is antisymmetric function. Okay. So, when the loading conditions and support conditions are symmetrical with respect to x axis passing through the center of the plate, then there is no need to retain any antisymmetric term on the deflected expression, deflection expression. So, therefore, in that case we can only retain the symmetric terms. Symmetric terms are say cos h, cos hyperbolic m pi a by a, and product of two antisymmetric term again is a symmetric. So, we can take these two term am cos hyperbolic m pi a y plus dmy sin hyperbolic m pi a y plus wp if the support condition and loadings are symmetrical. And if there is a condition that antisymmetry exists in respect of loading, that means in one side the loading is plus q, in another side loading is minus q and it varies linearly with 0 value at the center, then it is a antisymmetric loading. And in case of antisymmetric loading, we can take only the antisymmetric term. The antisymmetric term here you can note that y cos hyperbolic m pi a by y is antisymmetric. Why it is antisymmetric? Because y is a antisymmetric function and cos hyperbolic m pi a into y is a even function or a symmetric function. So, product of antisymmetric and symmetric function is again antisymmetric function. So, therefore, we can in that case we will retain this term, and sin hyperbolic m pi a y is a antisymmetric term. So, Cm sin hyperbolic m pi a into y, this term and this term along with this coefficient bmy and Cm have to be kept in case of antisymmetric loading. Okay. So, for symmetric cases am and dm are retained. For antisymmetrical cases the constant bm and Cm are kept. So, if we compare the two methods that we have learned so far, one is Navier method and another is Levy's method. Navier method is specifically applicable for a rectangular plate which has 4 edges simply supported. So, that is the condition that must be satisfied first, then we can use the Navier's method. So, both Levy and Navier's method are applicable for rectangular plate, that they have some general character, and both of this method actually use this trigonometric series, and both the methods yield the exact solution of the plate equations. So, that is some general character we have noted in case of Levy and Navier's method. But in Navier's method is applicable for rectangular plate whose 4 edges are simply supported, as I have repeatedly told this, whereas Levy's method is to be used when 2 opposite edges are simply supported. So, this is the difference, but it is not that Levy's method cannot be applied for Navier's condition. Levy's method can be applied when 4 edges are simply supported. So, Levy's method is more general compared to Navier's method. Navier's method yields deflected surface in the form of double trigonometric series, but Levy's method is based on single trigonometric series. Because of double summation, Navier's method is a slowly converging method, whereas Levy's method it uses single trigonometric series, therefore, it is fast converging, but the computation of in Levy's method is slightly involved compared to Navier's method. So, these are the major difference between the Navier's method and Levy's method for rectangular plate. Now, let us see a problem when the rectangular plate A cross B is the dimension and your thickness is h. So, that flexural rigidity D is E h cube divided by 12 1 minus mu square. Okay. The plate is loaded with this Q naught is the loading intensity per unit area. Okay. And since it is symmetrical, okay, so we pass the axis, x axis passing through the center of the edges which is parallel to y axis. So, the plate is symmetrical about the x axis, that you can see here, and these two opposite edges are simply supported, x is equal to 0, x is equal to a, and other two opposite edges y is equal to 0 and y is equal to b are also have the same conditions in the boundary, and that conditions are clamped, because clamped conditions are very common in case of plate, because in case of steel plate we weld the plate to the component, okay, maybe the flange of a column or this wave of a girder. Then we have the reinforced concrete slab, where the edges are the slab is supported by beam which is integrally built, that means monolithically cast. So, therefore, fixed condition develops at the end. So, fixed conditions are common and therefore, we cannot ignore this, and with the help of Levy's method we can easily encounter this condition. Okay. So, let us assume the deflection surface as y m y sin m pi x by a. Now, earlier we have seen that a solution is obtained in this form, but since in that case the condition that I am now discussing, that two opposite edges are clamped and two opposite edges are simply supported. So, in that case symmetry condition is satisfied, and therefore, we will take this term a m cos h m pi a by y and d m y sin h m pi a by y, and plus W p will be there because the plate is loaded. So, naturally this particular solution will also exist. Okay. So, now the solutions can be written in this form for y m y, that is a m cos hyperbolic m pi y by a plus d m y sin h m pi y by a. You can see this the term that I have written with the red color is a symmetric term specifying the homogeneous solution. Okay. But this term that is written with a blue color is a particular integral, because the loading is here constant. So, particular solution is also assumed as a constant, and after satisfying in the after substituting in the differential equation, the solution is obtained as this 4 q naught a to the power 4 divided by d pi to the power 5 m to the power 5. So, this particular solution is due to the load acting on the plate. Okay. Now, our requirement is that the boundary condition have to be satisfied. Okay. Now, on the boundary, that is y is equal to 0 and y is equal to plus minus b by 2. You see now the x axis is passing through the edges parallel to y axis. So, therefore, x is equal to plus b by 2 or x is equal to minus b by 2. X is equal to minus b by 2 is this edge if the direction of positive direction of y axis is upward here, then this is your this edge specified as y is equal to minus b by 2, and this is the edge specified with y is equal to plus b by 2. So, at both the edges, say y is equal to plus minus b by 2, the boundary condition is same. So, now we will apply the boundary condition at the two opposite edges. Okay. Now, boundary condition at edge y is equal to plus b by 2 or minus b by 2 requires use of derivative. Let us now physically understand the boundary condition of these two edges. Now, due to fixity, the slope will be 0 along the y axis. So, this del w by del y will be 0 and del w by del y will be 0, that means d capital Y m divided by dy equal to 0, and because of clamped condition the w is also 0, that is y is also 0. So, at y is equal to plus b by 2 and minus b by 2, boundary condition requires the function itself and its derivative up to third order maximum, because when we relate shear, that third order derivative is required. So, in these three equations I have given you the derivative of the function, because derivative can be easily computed from the function, this function y m y. First derivative you can see, because this is the constant term. So, derivative of this term with respect to y is 0, but when I differentiate this term with respect to y, it will be a m, then m pi a will come out as constant and cos hyperbolic will be converted to sin hyperbolic m pi y by a. Now, here you are getting product of two functions of y, one is y and another is sin hyperbolic m pi y by a. Because the product of two terms, when it is differentiated, it will give you say y. First if I differentiate with respect to y for the second term, then y m pi a cos hyperbolic m pi y by a plus, then I differentiate the first term, then differentiation of y with respect to y is 1. So, then sin hyperbolic m pi y by a. So, therefore, this condition you can see here that I have written after differentiating the y m y. Then differentiating this quantity again, this sin hyperbolic m pi y, this m pi y will come out. So, it will be square term m square pi square by a square, then a m, and sin hyperbolic will be converted to cos hyperbolic due to differentiation. So, cos hyperbolic m pi y by a, then the terms inside this second bracket that I will differentiate. Now, sin hyperbolic if I differentiate, then m pi a by cos hyperbolic m pi y by a, then this term if I differentiate, this is the constant term. So, I have taken it, and then this term y cos hyperbolic m pi y by a is differentiated term by term. First term is differentiated. So, with respect to y, so it is 1, then cos hyperbolic m pi y by a, then secondly it is differentiated with respect to cos hyperbolic with respect to y, this function, that cos hyperbolic m pi y by a is differentiated with respect to y, therefore, m pi a is coming out here, and then y remains as it is, and cos hyperbolic is transformed to sin hyperbolic m pi y by a. So, this is the second derivative. It is required to impose the bending moment condition at the edges. For simply supported edges, this is required, and also for spring supported edges we require bending moment to be 0. So, this derivative is important. Then if I differentiate further up to the third order, then here you can see that I differentiated this. So, m cube pi cube by a cube, this term is coming, and then m pi a already has come out inside the cos hyperbolic function, and then cos hyperbolic is transformed to sin hyperbolic y, sin hyperbolic m pi y by a, okay, plus d m. Now, inside this you are getting so many terms. So, you differentiate term by term. So, after differentiating and arranging some common terms, you will get this with sin hyperbolic m pi y by a, coefficients are this, and with y cos hyperbolic m pi y, coefficients are this. So, one important thing you can note here, that when we take the odd derivative, you can see the odd terms are appearing. So, sin hyperbolic m pi y is odd term. Here also you can see y cos hyperbolic m pi y is also odd term. Okay. So, then when we are differentiating with respect to second derivative, that is the even derivatives. So, you can see the even terms are appearing. So, cos hyperbolic m pi y by a, then here you can see this is even term, and here this is also even, and this is odd, and this is also odd. So, product of two odd function is again even function. So, with even derivatives, the even terms are associated. Then when again we go further higher derivative, say third derivative, then you can see that interestingly all the even terms appear. So, this sin hyperbolic m pi y by a is even odd terms appears. Okay. When we do the third derivative, the sin hyperbolic m pi y by a is odd term, then here you can see again sin hyperbolic is odd term, and here y is your odd term, but cos hyperbolic is even term. So, product of odd and even is again odd term. So, this interestingly it is noted that with odd number of derivatives, odd terms are appearing, with even number of derivatives, even terms are appearing. Okay. Now, apply boundary condition at y is equal to plus b by 2 or minus b by 2. So, I have chosen to apply the boundary condition at plus b by 2. So, y m at b by 2 equal to 0. Now, what is y m? If you see, y m was this function. Okay, that is the solution of the differential equation of this differential equation, okay, complete solution. So, if I apply the deflection boundary condition at y is equal to b by 2, you will get that instead of y I have substituted b by 2. So, m pi b divided by 2a. Similarly, on the other case with the dm, the original term was in terms of y was y sin m pi y by a. Now, instead of y I am putting b by 2. So, it will be dm b by 2 sin hyperbolic m pi b divided by 2a plus this particular integral due to loading. Okay. So, that is the boundary condition at y is equal to b by 2 at one of the edges. Then the claimed condition, that is the slope has to be 0. So, that I am now doing on the first derivative of the function. So, first derivative is this and that have to be 0 at y is equal to b by 2. Now, if you substitute y is equal to b by 2, you will get am this m pi a sin hyperbolic m pi b by 2a plus dm m pi b by 2a cos hyperbolic m pi b by 2a plus sin hyperbolic m pi b by 2a equal to 0. So, we have got this equation, this is number 1 equation and this is number 2 equations after applying the boundary conditions. Okay. After applying the boundary condition, the two equations that we got contains two unknown quantities, one is am and another is dm. So, two equations are solved simultaneously. The easiest and systematic method is Cramer's rule for such few numbers of variable. The linear equations with few variables, you can use up to 3 variables, you can use the Cramer's rule easily. So, using the Cramer's rule, we can write the solution for the two equations 1 and 2 that are obtained using the boundary condition. So, am is equal to delta 1 by delta and dm is equal to delta 2 by delta. Now, the denominator delta is the determinant formed by the coefficient of this am and dm of the two equations that are obtained applying the boundary condition. So, first coefficient for forming the determinant delta, the coefficient of am in the first equation is cos hyperbolic m pi b by 2a. So, therefore, cos hyperbolic m pi b by 2a, that is the first term in the first row. Second first term, first row, first column, that is the term. Then this term if you see b by 2 sin hyperbolic m pi b by 2a. So, this will appear here. Okay. Similarly, systematically this will appear in this term and this whatever inside this second bracket, it will go in the position 2 by 2, that is this second row, second column. So, this delta has to be evaluated. Okay. This delta evaluated and this is this has to be non-zero, otherwise solution will not be bounded. So, after evaluating this delta, we can find this quantity as delta. Then one interesting thing you can see that these two functions can be combined, because you know that the relation cos hyperbolic m pi b by 2a minus sin hyperbolic m pi by 2a is 1. So, therefore, we have combined these two function, this term and this term, and this is the term and other term is as this. So, this is the delta. Now, delta 1 can be obtained very easily after expanding the determinant. If I expand the determinant, then it is minus q naught a to the power 4 d pi to the power 5 m 5 and this is. So, this can be multiplied and this will be 0. So, delta 1 is easily found out as this quantity. So, am will be delta 1 by delta. So, this term is there and you can see that this is the delta, this determinant formed by the coefficient of the two equations, coefficient of the variable am and dm in two equation formed after applying the boundary conditions. Okay. So, after finding am, you can find the dm another constant by finding the delta 2. So, when we find the delta 2 by Cramer's rule, you can see that the coefficient or the elements have to be replaced by the non-homogeneous term like that. So, delta 2 is here, this we are finding this dm coefficient dm using the delta 2. So, in place where the dm appears, that is the second place, the non-homogeneous term in the first equation is minus 4 q naught a to the power 4 divided by d pi to the power 5 m to the power 5. I mean the terms in the right hand side is put here, and in the second equation it is found from the slope condition. That means, the forcing function which was constant does not appear in the slope equation. So, therefore, this term is 0 here and it is appearing in the second column, second row. Okay. So, this is delta 2, and after expanding this, you can see this goes to 0 and this is coming as this. Okay. This will be minus, but again minus minus will be plus. So, this quantity is written as this. So, after finding delta 1 and delta 2, dm is found. So, once you find am and dm, you can easily find out the deflected series as am cos hyperbolic m pi y by 2a dm y sin hyperbolic m pi y by 2a plus this is the non-homogeneous term and multiplied by the sin m pi x by a. So, this is the complete deflection series. So, when you find the deflected series, then you can go for finding the bending moment. The bending moment that are of most important is the fixed end moment, which will be more than the midspan moment. So, here the negative moment that occurs in the fixed end can be found out that in the x direction as well as in the y direction by using this quantity, that minus d del square w del x square plus mu, mu is the Poisson ratio del square w by del y square. So, m x is found out. Similarly, m y can be found out, but in the expression of m x you can substitute all the quantities and then you can find the value of m x and m y. So, at the fixed edge y is equal to b by 2 or minus b by 2, we get the bending moment m x and m y per unit length as the case may be. Now, let us discuss another problem of plate which has all the edges simply supported and it is loaded by UDL not up to the full extent of the plate, but up to the middle area. So, it covers only a by 2 length of the plate. So, plate length is a and the width is b. Now, again you can note here that the plate is symmetrical about the your x axis. So, therefore, I write this equation with the symmetric terms again. So, symmetric terms is taken, okay, and W p is the particular integral. Now, here the W p is obtained as the integral of 2 by a d into q naught sin m pi x by a dx, but the limit of integral you can see because of the presence of the load up to the middle portion of the plate, the upper limit of the integral is changed to a by 2. So, putting this limit and evaluating the integral, we get this this f m y is 2 q naught d m pi 1 minus cos m pi by 2, and you can see this integral gives you very interesting results. Means when m is equal to the odd integers 1, 3, 5, then this value will be 2 q naught divided by d m pi, and when the values are 2, 6, 10, then you will get 4 q naught d m pi, and when the m is 4, 8, 12, you will get the value of the integral as 0. Okay. So, for the above cases W p is obtained as, since again your this f m y, that is the this function is again a constant. So, we can assume that particular solution is also constant. So, substituting the particular integral as constant, in this differential equation, you can see this term has no significance, this term has also no significance, only here m to the power 4 pi to the power 4 divided by a to the power 4 in some constant, which is the particular integral w p equal to this term that we have evaluated. Okay. So, after carrying out this integral, we can find a particular integral in this term 2 q naught a to the power 4, okay, a to the power 4 will come here, and here it will be m to the power 5 pi to the power 5 and d will be there, and this term inside the first bracket will exist 1 minus cos m pi by 2, depending on the different values of m, this will be evaluated. So, after finding the complete solution of y m, we can now write this series as a m cos hyperbolic m pi y by a plus b m y sin hyperbolic m pi y by a plus 2 q naught a to the power 4 divided by d m to the power 5 pi to the power 5 1 minus cos m pi by 2 into sin m pi x by a. So, this is the expression for the deflected series. Once you get the deflected series, you can go for finding this your bending moment and shear force etcetera, whatever you like. Okay. Now, let us come to another problem, because the boundaries are taken as simply supported condition. So, two conditions have to be imposed, one is your deflection condition and another is curvature condition in this problem, and since we have derived the second derivative of the function already in few occasions. So, that results can be applied, that the second derivative expression can be applied here to impose the boundary conditions on the other two edges which are simply supported for this problem, and you will be able to find this constant a m and d m, and then all other quantities, that is bending moment, shear force, can be evaluated. Okay. Now, let us consider another problem of plate which has a loading q naught per unit length, but it is not a distributed means in the sense that it is not distributed over the area. It is only a line load, that you can call it strip loading, and this loading acts along the y direction, and you can see that this loading is situated at this a by 2, and it is continuous along the y axis, continuous along the y axis. So, that means I can represent this loading with the help of direct delta function, because this is a line loading, and this line loading is only meaningful when this x is only equal to a by 2. In other points there is no line loading. So, I can express this loading as q naught direct delta x minus a by 2. So, after substituting this loading function into this f m y, that is required to find out the non-homogeneous term of differential equation, we get that this function, and by virtue of this property of the direct delta function, we can now easily write that 2 q naught a by d, where q naught is a constant, and sin m pi by 2. So, this result is again meaningful when m is equal to 1, 3, 5 etcetera. For odd integers, this value will be not be in existence. Okay. Because this is again a symmetrical plate problem. So, I can now write this function as y m y, a m cos hyperbolic y by a, d m y sin hyperbolic y plus y p. Y p is the particular integral or particular solution of the equation. Okay. Now, again here you can see the f m y is a constant, f m y is a constant term which varies with m. Okay. So, therefore, I have assumed this particular integral is also constant. So, w p, let w p be c. Okay. So, after substituting this particular integral in this differential equation, we readily get what is the value of c. So, value of particular integral, that is c, is evaluated here, and after substituting this, we can get the full solution for ym and then series, and applying boundary condition. Suppose I have taken here the fixed end, okay. Two ends are fixed. If I take the two ends are fixed, then I apply the boundary condition of the fixed end. Boundary condition of the fixed end is say y m equal to 0, and then y m is equal to 0 at y is equal to plus b by 2 or minus b by 2, and dy m by dy equal to 0 at y is equal to plus b by 2 or minus b by 2. Any edge you can take, because the same condition exists in both the edges. So, when we substitute these two conditions as usual we obtained in the earlier cases, then we get two simultaneous equations, linear equations with unknown variable a m and d m. So, it can be solved easily by any method. So, I have illustrated this the systematic method known as a Cramer's rule, that you can use by expanding the determinant that I have shown, and then you can obtain the constant a m and d m completely. So, when you obtain the a m and d m, your problem is known, that means deflection series is completely known, and then after obtaining the deflection you can explore other quantities. That means, if you want this further say bending moment, shear force, you can derive it from the deflected quantities. Okay. So, now I want to show you how some other problem can be tackled with the help of this Levy's method. So, first problem is let us take a square plate whose dimension is a cross a and has two opposite edges simply supported and other two opposite edges clamped. The plate carries load that varies sinusoidally as q x y equal to q naught sin pi x into sin pi y by a. So, our question is that deflected surface has to be found out. Okay. Second question we will see a plate of dimension a cross a. This has its three edges, x is equal to 0, y is equal to 0 and x is equal to a are simply supported, but y is equal to 0 edge is clamped and other edge y is equal to b edge is also clamped. So, let us formulate an exact solution using the Levy's method to find out the deflected surface of the plate when there is uniformly distributed load acting on the entire area. Okay. So, let us solve this problem and show you the how this problem can be tackled using the method that we have learned in Levy's condition. Okay. So, first problem is this. Problem 1, we have a rectangular plate okay, but two sides are equal. For simplicity we have taken two sides are equal and two opposite edges are simply supported, but other two opposite edges are clamped. So, again this problem is a symmetric problem. So, I can now take the x axis here, x axis, and y axis say this. Okay. The plate is loaded sinusoidally, that means if I see the variation along x axis, the variation is sinusoidal. The amplitude is q naught. Okay. Then if I see the variation along y axis, again it is sinusoidal. So, in the two direction load is sinusoidal, that means if I write the load function, that can be written as q x y is equal to say intensity is q naught sin pi x by a sin pi y by a, because it is a square plate. So, the dimension of the plate is a by a. Okay. Now, because of symmetrical problem, we take the term in the deflected series y m. Deflected series is this summation of this y m y sin m pi x by a, and y m y, you know, because of symmetry, that only symmetrical terms have to be taken. So, the differential equation that we need to solve, that I illustrated, and the solution is y m y is equal to a m cos hyperbolic m pi y by a plus d m y sin hyperbolic m pi y by a plus particular integral. Okay. Now, particular integral has to be found in that case, because it is not uniformly distributed load. So, the result is known to us. Okay. The particular integral has to be found from this function, that is given as 2 by a d. D is the fractal rigidity of the plate, and the integration 0 to a q x y sin m pi x by a into dx. Okay. Now, here the q x y is this function, q x y is given here as the distributed load in the form of the sinusoidal function. So, twice a d, amplitude of the loading is q naught. I have taken it as a constant and taken outside the integral sign. So, inside the integral we have this function. Now, this integral can be easily carried out, because you see, first let us because this is a function of x. So, only the integration with respect to x is meaningful. So, sin pi y by a will appear as a constant. So, now if I integrate this sin m pi x by a, sin m pi x by a, that is 0, only it is meaningful non-zero when m is equal to 1. So, taking m is equal to 1, that integration can be carried out twice a d, and you will get this integration as 0 to a sin square pi x by a dx, and then sin pi y by a will appear as it is, as a function. So, ultimately that you are getting f m y is equal to your this twice q naught a d into this will be a by 2 and sin pi y by a. So, this result will be your this a will get cancelled, q naught by d sin pi y by a. So, this is our the function f m y. So, now we can go forward to calculate this particular integral. So, particular integral is now calculated. We take the differential equation, differential equation was this for m is equal to 1. Now, instead of f m y, now we have got this particular integral. So, that value I will substitute here. In the earlier case we got q naught by d sin pi y by a. So, solution for y is, because it is a symmetrical again. So, a m cos hyperbolic pi y by a. It is not necessary to take any integer value of this, not to expand it, because it is meaningful only when m is equal to 1. So, therefore, a 1, okay, I am writing a 1 directly, then d 1 y sin hyperbolic, because this is product of two odd function plus particular integral. this is y. Now, because this is a forcing function again is a sinusoidal function. So, let us assume particular integral as also some constant C 1 sin pi y by a. Okay. Now, you can see that after substituting this value here, you will get that this particular integral will appear as a very simple term, that I will give you this term to you. So, W p is now appearing as q naught a to the power 4 pi to the power 4 d sin pi y by a, because C 1 is now this quantity. How this C 1 is found? That assume particular integral as this C 1 into this and substitute this in the differential equation, and then equate the like terms, coefficient of like terms. So, you will get C 1 as this value. So, total solution is now we can write y is equal to a 1 cos hyperbolic pi y by a plus d 1 y sin hyperbolic pi y by a plus this q naught a to the power 4 pi to the power 4 d sin pi y by a. So, this is the complete solution of y. Now, let us impose the boundary condition to determine the constant a 1 and d 1. Okay. That can be imposed by giving the two conditions, that y is equal to a by 2, that deflection is 0 and slope is 0. So, since the plate was clamped along two other edges, this is clamped condition, this is also clamped, and this a by 2, and this is also a by 2, and this is simply supported. Okay. And this length is also I am taking as a, because it is a square plate. Okay. So, imposing the boundary condition at y is equal to a by 2, capital Y is 0, that gives you that a 1 cos hyperbolic. If you substitute this y is equal to a by 2, then cos hyperbolic pi by 2 will come. So, let us assume take it alpha 1 is equal to pi by 2. So, just to simplify the calculation I have taken this. Okay. So, this is coming. So, after substituting this y is equal to a by 2, first term in this deflection equation is this, then second term will come as d 1, okay, d 1 a by 2, because y is there. So, a by 2 and sin hyperbolic again pi by 2. So, alpha 1 equal to this your non-homogeneous term. If you see here that sin pi y by a was there. So, instead of y you put a by 2. So, sin pi by 2 is 1. So, therefore, this term will be minus q naught a to the power 4 by pi to the power 4 d. Okay. So, that is one equation. Okay. Second equation we will get at y is equal to a by 2 y dashed, that is the first derivative, dy by dy equal to 0. So, using the first derivative equation we get here say a 1 pi by a sin hyperbolic alpha 1 plus derivative that we will do is a product of two function earlier, the coefficient variable associated with d 1. So, you get two terms sin hyperbolic alpha 1 plus alpha 1 cos hyperbolic alpha 1 equal to 0, because the derivative of constant that requires there will be 0. So, this is your first equation and this is your second equation after application of boundary condition. So, A1 and B1 can be solved. A1 is equal to say delta 1 by delta, and D1 will be delta 2 by delta. Delta is a determinant that is formed by the coefficient of A1 and D1. So, let us see coefficient of A1 is cos hyperbolic alpha 1 and coefficient of D1 is A by 2 sin hyperbolic alpha 1. Then coefficient of here A1 in the second equation pi by A sin hyperbolic alpha 1, and coefficient of D1 in the second equation will be sin hyperbolic alpha 1 cos hyperbolic alpha 1. Okay. So, this is the delta. Similarly, you can find delta 1 as this. Let us write down the delta 1. Delta 1 will be minus q naught a to the power 4 pi to the power 4 d. Here it will be 0. Then here in this case it will be a by 2 sin hyperbolic alpha 1, and in that case it will be sin hyperbolic alpha 1 plus alpha 1 cos hyperbolic alpha 1. Okay. Mind that alpha 1 is pi by 2. Okay. So, delta 1 is this. You can easily evaluate this. The determinant will be q naught a to the power 4 pi to the power 4 into d, then multiplied by sin hyperbolic alpha 1 plus alpha 1 cos hyperbolic alpha 1. So, this is delta 1, and delta 2 can be similarly found out, and delta 2 will be cos hyperbolic alpha 1 pi by a sin hyperbolic alpha 1, and this term will be same as this. So, q naught a to the power 4 divided by pi to the power 4 d, and this is 0. So, after expanding you will get this term as q naught a to the power cube divided by pi cube d sin hyperbolic alpha 1. Okay. So, we got delta 1 and delta 2. Now, we can get A1 as delta 1 divided by delta and D1 as delta 2 divided by delta. Once this A1 and D1 is known, then deflection series is simply calculated as that is because only m is equal to 1 is important here, and other term it does not exist. So, we will write this A1 cos hyperbolic pi y by a plus D1 into y sin hyperbolic pi y by a multiplied by sin pi x by a. So, this is the deflected series, and substitute A1 from here and substitute D1 from here. So, complete deflection is known. Maximum deflection will be at the center of the plate when x is equal to a by 2 and y is equal to a by 2. Okay. So, this is one problem that I wanted to discuss, and that is solved with the help of Lebesgue method. Second problem, let us consider a general problem which has a completely unsymmetrical condition. So, unsymmetrical condition, the problem 2. We have this rectangular plate let the length is a and the width is b, and it has two opposite edges simply supported, that must be there, otherwise we cannot apply Lebesgue method. In addition, the boundary condition and other two edges at x is equal to y is equal to 0 edge again simply supported, and here we have taken fixed edge. Okay. So, now you can see this is simply supported this is simply supported, this is simply supported and this is clamped. Because of the purely unsymmetrical nature, we cannot take any advantage of symmetry, that means omitting two constants and taking and retaining two constants, that business cannot be done here. So, what we do here, we take the axis as it is, this is x axis and y axis, and we have to kept the full term of the deflected series, that is y m y was composed of a m plus b m y cos hyperbolic m pi y by a plus c m plus d m y sin hyperbolic m pi y by a. Okay. So, these four constants we have to take, there is no other way, because the boundary condition is purely unsymmetrical. Now, we have to apply the boundary condition one by one. So, at y is equal to 0, deflection is 0. Of course, your this particular integral will come. So, particular integral value will be same for uniformly distributed load that we have found out earlier, and this particular integral I am writing here for uniformly distributed load, it is 4 q naught a to the power 4 divided by d m to the power 5 pi to the power 5. Okay. So, this particular integral has to be written here. So, at y is equal to 0, y m actually y m 0 is 0. Okay. Y m. So, substituting the value of this y is equal to 0, because cos hyperbolic 0 is 1 and sin hyperbolic 0 is 0. So, therefore, we get here this a m, and here you will get this term will vanish, equal to minus 4 q naught a to the power 4 d m to the power 5 pi to the power 5. So, one constant is known by application of this, and second constant, other constant you have to find out applying the boundary condition. So, applying the boundary condition on bending moment, that at y is equal to 0, second derivative of y is also 0. Okay. So, that condition gives you the equation, that will be slightly larger equation, but it can be computed very easily, there is no doubt. So, a m m square pi square by a square cos hyperbolic m pi y by a plus b m m pi by a sin hyperbolic m pi y by a plus m pi by a sin hyperbolic m pi y by a plus y m square pi square by a square cos hyperbolic m pi y by a. So, this is expansion of b m, then on this c m you will get c m m square pi square by a square sin hyperbolic m pi y by a, and on d m again you will get the terms m pi by a cos hyperbolic m pi y by a plus m square pi square by a square y sin hyperbolic m pi y by a plus m pi by a cos hyperbolic m pi y by a. So, this is the second derivative and it is 0 at y is equal to 0. So, substituting this value, you can easily see that this function exists, but here you see sin 0 is sin hyperbolic 0 is 0, and this is again y into something is 0, y is 0. So, this is going to be 0. Okay. Then here this is going to be 0, and here you will find that with dm this is 1 and this is going to be 0 and this is 1. So, ultimately you will get am square pi square by a square plus 2 m pi by a dm equal to 0. Now, since am is calculated earlier, we can now get the dm. After getting dm, and dm of course, I am writing this value of dm, dm will be 2 q naught a to the power cube divided by d pi to the power 4 a to the power m to the power 4 m to the power 4. So, value of dm is this 2 q naught a cube d pi 4 pi to the power 4 and m to the power 4. Okay. So, two constant am and dm are known. Other two constant will be found out applying the boundary condition at these edges, that is clamped edges. At clamped edges, that is y is equal to b, apply this equation and dy by dy, capital Y of course, at b equal to 0. By using these two equations, you will be able to get these two constants am and bm. So, using this two constants, other two constants say bm and cm can be found. So, these two conditions will give you two equations again with bm and cm, because am and dm are already evaluated. So, now you get the 4 constants of integration that is resulted due to unsymmetrical condition of boundary. So, therefore, the solution is now known completely with this series. Okay. So, complete series is now known because am, bm, cm, dm are calculated. So, in this way we can handle any unsymmetrical condition, only the computational effort may increase, definitely will increase because of 4 constants involved. Okay. So, what I want to tell you that in conclusion, the Levy's method is applied for rectangular plate when two opposite edges are simply supported and other two edges may have any boundary condition, and it yields the exact solution of the plate problem. That is first thing what we learned from the Levy's method. But if we compare the other exact method, that is Navier method, that is restricted only to the simply supported boundary conditions along all edges. So, Levy's method is more general, and because of the use of only the single sign series, the calculative effort is less, that is computational effort is less, only the derivation part is slightly longer, because in the intermediate step you have to solve one differential equation, ordinary differential equation, which will yield you the unknown function y, but with 4 constants of integration that have to be found by using the conditions at the boundary on the other edges. So, two methods that we have learned now, Navier's method and Levy's method, can be successfully applied to the plate problem for specific boundary condition, and it yields the analytic solution. In most of the cases, the loading is uniformly distributed load, and we have seen that for uniformly distributed load, the exact solution is very much in agreement. The solution obtained by Levy's method is in very much well agreement with the Navier's method. So, with this I conclude, then we will see what are the other applications of Levy's method. So, we will investigate whether Levy's method can be used indirectly to solve the conditions not met in the Levy's boundary condition. That is, suppose a plate with all edges are fixed, can we use, the question is, can we use the Levy's method for such plate? We will discuss this in the next class. Thank you very much.